Great, Alyssa. Thank you. Thank you, everybody, for tuning in. So I'm Shweata and Hegde, and today we are here to talk about how Wikidata has been supporting CV Open, which is an open student research project in plant chemistry. So just so that I would like to spend 1 or 2 minutes talking about CV Open so that we have some time for people to join in. So CV Open was started in 2019 and it's a collaboration of 3 different projects. One is Content Mine, which was started by Peter Murray-Rust, who's here with us today. And then SOLDB, which is a database that Dr. Anjali Yadav and others run. And also Very Clear, which is a company which Emmanuel Ferreira runs in Brazil. So that's what CV Open stands for: Content Mine, SOLDB, and Very Clear. And we are looking at essential oil literature. So essential oil, for people who don't know, is basically the chemical that you extract from plants, and they're usually very fragrant. So with that, I think let's go ahead with the presentation. So today we are concentrating on, as I said, how Wikidata has been supporting CV Open, and we're especially interested in plant chemistry. So a little bit about me. I'm a third-year science undergrad, life science undergrad here in India, and I have been a part of CV Open for about a year now, and I've also been working on a natural language processing project. More about it in the very end of the presentation. So the rough architecture of the presentation is going to be the following. I will talk about why we are interested in plant chemistry in the first place, and second, talk about the toolkit and give you a brief overview of the workflow, and third, introduce you to our career interns. Some of them are here with us today, and then they will then take over and demo some of the tools and share their experiences and challenges. Just as a side note, all the presentations from the career interns are pre-recorded. Since they're on 4 lines, we went ahead and pre-recorded their sessions, which I will play after my part. Okay, so with that, let's get started. So first of all, why are we interested in plant chemistry? Simply put, plants are better chemists than we are. Plants basically use chemicals for literally everything, which includes communication, defense, attracting pollinators, and so on. So we are specifically interested in terpenes. So what's special about terpenes is that they all have the same starter molecule, which is isoprene. And based on what enzyme or the catalyst acts on the starter molecule, the final product, the final terpene is different. So that's how you get 20,000 or even more wide array of different kinds of terpenes. So we are looking at terpenes of some specific crops like corn, tomato, tea, mint, lemon, and grapes. And we are asking questions like, what are the enzymes involved in the synthesis of terpenes, and what are its corresponding genes, and so on. Given so thanks to the recent advancement, there is a deluge of information about genes and genomics in the scientific literature. However, we aren't making full use of it because it is so huge, right? And that's where machines can help us. And that's what we've been doing at CV Open. But before we even go ahead and talk about our tools, I wanted to zoom out a little bit and talk about how big the scientific literature is. So let's say you printed out a year's worth of scientific publication and stacked them all up. It would probably reach a height greater than that of Mount Everest. But sadly, you cannot make use of all of what's out there. So we are sadly restricted to just the 30% of open access papers in order to extract knowledge and seek answers for the questions we have. So now that we know that we have to look at the open access papers, the next question is that, how would I even read such huge amount of literature, right? So if let's say I'm interested in terpene synthesis, there are thousands of papers. I need to first find and download these papers. Second, somehow read all of what's out there and annotate them. And based on my readings, I then have to comprehend, interpret, and infer such huge amount of data again. So that is such a Herculean task, right? And that's where CV Open tools can help us. So we've been developing tools which can automatically download papers from open repositories like EuroPMC. And we've also developed a toolkit called AMI, which creates a dictionary, which is a set of terms from open structured databases like Wikidata, and B, use those terms to automatically annotate the scientific literature, and C, make inferences based on the annotations that we make. So just as I said, dictionaries are our mining tools, and we create all of our dictionaries from Wikidata. So we have created a ton of dictionaries, both at Open Virus and CV Open, including country, disease, drugs, funders, and so on. And all of these dictionaries are multilingual, thanks to the fact that Wikidata also catalogs information in many, many, many languages. So this is a typical example of how a dictionary looks like. With that, I would like to introduce you to the basic workflow, which I just described. So we first create dictionaries, then download the literature, and third, search the literature using these dictionaries, and the annotations can then be linked back to Wikimedia. So you will see this workflow throughout the presentation. So with that, I would like to hand it over to our Karya interns. Before I hand it over to them, a little bit about Karya. It is a program which is run by DST Rajasthan, wherein the young researchers get to work on a real scientific project like ours. And that's how we've onboarded these 4 interns. With that, I would ask you to grab a cup of tea, or a cup full of terpenes, I should say, and enjoy the rest of the recorded presentation. Thank you everybody for listening in. Okay, let me now switch back to my slides. Okay. So all the interns have now spoken about their experiences and challenges, and apart from that, given us the demo of our tools. So I would just like to reiterate the fact that we work in the open, and we follow open notebook philosophy, wherein we document each and every step as we go, and that includes all the problems, all our successes, and so on. And on each problem, we always try to solve communally. And this is like a traffic light spreadsheet that we had during Open Virus project, where we kept track of what each and everyone were doing in the open. So also to just to reiterate the workflow as well. So as Anjali and Prachi have shown us, we create our dictionaries directly from Wikidata. We mostly use Sparkle queries to create these dictionaries, and we then download literature, hundreds or even thousands of papers, by using a tool called Pygate Papers. And we then search the literature using these dictionaries to get full data tables, or dashboards, as we say, and also co-occurrences, which then link back to Wikipedia. So taking this a little further, we've also been able to use these dictionaries to get specific sections of the paper, and then from those sections of the paper, by using natural language processing and machine learning, tease out some terms which weren't present in Wikidata. So what we can then do is that we could then take these terms in bulk and put it back to Wikidata, thereby building a feedback loop. So this is the work that we've been doing with Daniel Meechan, who is also running a session parallelly in room 3. He might perhaps talk about it. So with that, I would like to thank all of the team, and especially our mentors, Dr. Peter Mararast and Dr. Gitanjali Yadav. So here's the team. Thank you, everybody, for listening in. We would also like to thank NIPGR and DST Rajasthan for giving all the interns the opportunity. And of course, we'd like to thank all the global volunteers involved in our project and the Wikimedia community. So thank you, everybody, and we're closing it down and are open to questions.
Shweata, thank you so much for the presentation. I'm wondering what's next for your project. I'm sorry for my voice.
No problem. I think Peter can take this up. He has been talking about so many exciting things. I think it's best answered by Peter. Peter, if you're here, you could answer Alyssa's question.
Can you hear me,
Yes.
Shani?
Yes.
This is a project which has a number of short-term internships at NIPGR in Delhi. The history of it is about 3 years ago, we actually got a grant from Wikimedia to build dictionaries. And then we created this and proved this concept. We're not funded in this project other than by having internships in NIPGR, and actually, of course, in at the moment doesn't mean physically in. It means that we can meet like this. The great thing is that this is now expandable, so we welcome anybody to come into this. We're so excited that just literally in the last 20 minutes, we've met up with Grunstedt and Egon Billighagen and others who have got a massive project in Lotus using Wikimedia, Wikidata, and it looks as if we are a perfect fit for them. So the potential of downloading papers from the literature is huge. And I think this scales to many, many Wikimedia projects, particularly in science, I would say.
Very exciting. I hope you keep us posted.
We will.
Okay, then I'm looking at the Etherpad for questions. I think we've covered it all. Alyssa, are there any questions that we have missed?
Shweata, can you hear me?
Yes.
Yes, hello. So first, many thanks for your exciting presentation. As said Peter, I think indeed, well, there could be a lot of very interesting overlap. In this project of Lotus, what we wanted to do is to share natural products occurrence that we found within the literature. And I had a question for you, because so what we did in our case, we didn't do any text mining. So basically we took pre-formatted databases documenting occurrence of a given natural product and its biological source. And we have found in the phase of manual curation and evaluation of these occurrences that, for example, in some databases that were built using text mining, we find things like, small example, people have been using a specific set of terpenes and benchmarking biological activity on Trypanosoma cruzi. And the reported occurrence is these terpenes and Trypanosoma cruzi, because there has been the biological term of Trypanosoma cruzi and the terpene, but in fact, the terpenes are coming from another plant. How do you deal with these cases? Because in a large number of papers, well, I guess this will happen. Also, you have the biological source indeed mentioned as a scientific name, but also, for example, biological targets.
Right. Okay. So, so what we've done with our tool doc analysis is that we've been able to pull out specific sections of a paper, let's say the introduction or the methods. And we also rely on creating a dictionary or a set of terms which commonly occur. Let's say this particular terpene was extracted from, and whatever word comes, whatever the phrase comes next might be the organism of our interest or from where it might have come from. We use such heuristics in order to, get the right information. But I do realize that it is a problem. Maybe Peter can add more.
Well, I think we're changing sessions, but just to say that we're actually going to use natural language processing at a sentence level so that we can resolve many of these relationships.
Okay, many thanks. Well, Peter and Shweata and well, all the teams there, I guess that we will keep in touch, and
Definitely.
thanks again, and bravo for all this tremendous work.
Thank you. Okay, thanks everybody for tuning in.